Hello everyone. So in today's topic is backtracking, graph coloring and Hamiltonian cycles. So contents are introduction to backtracking, terminology used in backtracking, backtracking algorithm, solving the graph coloring problem using backtracking approach, applications of graph coloring problem, Hamiltonian cycle, and finding the Hamiltonian cycle using the backtracking approach. Okay, so what is the introduction to backtracking approach means? Suppose we have a series of decision to make, okay, for a given problem, and we are finding the solution for that problem. Okay, what are possible solutions we have for that problem? Okay, so if you don't have enough information to know what to choose, and if each decision leads to a new set of choices or some sequence of choices may be solution to our problem. So all this we take care of in this backtracking approach. So backtracking is nothing but it is a methodological way of finding out various sequence of decisions we have for a given problem that gives us the result, okay, or that gives us the solution for that given problem. So here you can see we have an animation here. So in this we have start. If you start from one end, okay, that is called a start. So from start we go towards one path, or we can say one direction, so to find our solution for a given problem. So if you see we get a dead end, so we again come back to our previous, so it's called as backtracking, coming back to its previous where we have left node or path, we can say, again traverse all possible path that it has. If there is again a dead end, so again come back, again visit to the next path or next vertex that is not yet visited, and proceed in the same way. If we find a dead end, again come back, again proceed to the next path. If we find again there is no possible way or dead end, so again come back, and again it will finally we will reach to the our success. So this is all the backtracking. If we are not able to get back our solution, so that is called as a dead end. We are not allowed to go further from that point, so come back to its previous point. So we are backtracking to our path that we have followed. Okay, so this is the simple principle of backtracking, how it is does. So we can say it is a depth first search like approach. Okay, now terminology used in backtracking. So we know we have a in a tree we have nodes. Okay, so there are three kinds of node. We have a root node, then we have some internal nodes, and we have some leaf nodes. So backtracking is nothing but we are drawing a tree, we are searching a tree to find our goal leaf node. So where is our success leaf node is that, so we are finding that leaf node. So here you can see we have one root node colored in green, and we have some green internal nodes, and we have some red ones that is called leaf nodes. Okay, so we have nothing but we have a tree like structures, and we are doing the depth first search approach to get our best solution, okay, for this given problem. So each leaf node that we have in the tree, that is the parent of one or other nodes, okay, that's called children. So we know each node in the tree other than the root node has exactly one parent. So parent is there, and parent can have many children. So we can draw this way in downward also, parent and their children. Okay, so this is the basic principle of tree that we use for backtracking. Now how does this backtracking algorithm works means, suppose we have the basic algorithm. So simply we are exploring each and every node one by one. Okay, step by step we are exploring each and every node for finding our success node. So to explore a given node n, so first we will check if that node n is a goal node or not. So if it is there, so we return success. Else if it is a leaf node, so then we are not got this success, there is written a failure. So if for each child of that node, so again explore the children of that node, that means we are going towards the depth from that node. So and again if that children of that given node is our desired node or desired path, we can say, that is called our successful path, so we will return success. So else we can return failure if you don't find our correct or suitable path. Okay, so this is the simple backtracking algorithm. So just going deep into deep or depth first search, okay, like this approach. Now one of the most important application of that backtracking is graph coloring problem. Okay, so what is graph coloring problem actually is means it is a classical coloring problem. Given a graph G having some n nodes, and we have some colors, okay, So we need to color that graph with that given colors. Okay, so what is the condition is that, so no two adjacent or neighboring vertices can have the same color. This is the rule. So no two adjacent vertices or node can have the same color. Now if we'll see some examples of graph coloring problem. Okay, before this there are some problems that we are finding or that we are solving in graph coloring problems. The first is called as M color decision problem. What do you mean by M color means? So given a graph and given a some colors we have, so without applying directly that color to the graph, we are simply checking whether we can color our graph with this given colors or not. So that is called as M coloring decision problem. That is a decision problem. Okay, given the color and the corresponding graph, so can we use that color or can we color the graph using the given color? That is called as decision problem. And the second one is called as optimization problem. That is called M coloring optimization problem. Okay, so given a graph, so in how many minimum number of colors we can color that graph, so that is called as optimization M problem. So that is also known as chromatic number of a given graph. So what do you mean by chromatic number? The minimum number of colors that are required to color a given graph. So that is known as chromatic number of a graph. Okay, we will see some examples. So here you can see we have a graph having 4 vertices. Okay, so let's take the value of M. Let's take the value of M as, okay, let's take the value of M as, so here I am taking the color as M. So if you take a 2, can we color this graph using two colors? It's not possible because all are adjacent, so it will disobey the rule. So we can't color it with 2 colors. So let's try with 3. Okay, can we color this graph with 3 colors? Okay, so let's erase this one. Yes, let's take a 3 color. Okay, so we have this 3 color that I'm taking as M value. So the colors are suppose red, green and blue, RGB. Okay, so let's try to color. So if you color, if you take the first node 1 as color, if you color with red, suppose I am coloring this node 1 with red, so then this 2 can be colored with green, and then this 4 can be colored with blue. Okay, and can we color this with which color? We can't use red here because it will become adjacent. We can't use blue because it will become adjacent. The only choice left is green, so we can do this. Okay, here you can see no two vertices or no two edge have the same color. Okay, no, so this is called the this. Yes, we can use this. So we have, with the help of 3 colors, we have colored the graph, and the ordering are red for 1, green for vertex 2, then we have blue for vertex 4, and we have 3, there is a green for vertex 3. So this is the our solution. So like this we can have many solutions. Okay, so how many solutions are there for a given graph, for coloring the given graph? So that is we solve using the backtracking. Okay, now suppose we have this graph. Let's take one more graph having 4 vertices, 1, 2, 3 and 4. Okay, so and we have the M value as 3, so color are red, green and blue. So the I have written it, and the time taken for coloring the graph is M to the power n minus 1, where M is the color and n is the number of nodes in the graph. So before analyzing this, we have to first study the that is called as a state space tree. Okay, so how to draw the state space tree for this given graph? So here you can see, so I am going to draw here. Okay, so suppose this is our first node, that is our node number 1. So this, if I color this, what are different possibility for coloring this one node? So there are 3 possibilities. Okay, either I can color this with red, or I can color with green, or I can color with blue. So there are 3 possibilities to color this graph, to color this first node 1. Okay, so okay, we are at this node number 2. For this node number 2, again we have how many possibilities? We have again 3 possibility. Just I am taking the utmost condition. Okay, I am not just now following the adjacent rule for coloring the graph. So at most how many colors for a given node in this graph is there. So I'm taking the overall this state space structure. Okay, for second node, so again for coloring the second node, again I have red color, green color, blue color, like this. Again for this this one this node, first node, again if I color with green, again we have different RGB, I can color with different color. If I color with blue, again I have different options to color the second node, that is the red, green and blue, like this. So like this, first node, second node is colored. Taking the third node, if you how we can color with third node means, so there are again three different possibilities are there, that is red color, green color and blue color, like this. Again it will, this node also will have, can be colored with three ways, that is red, green and blue. Like this we will keep on doing for all the nodes. So if you see the total how many possible colors we have used for coloring the graph means, so this is our state, this is our state space, we can say tree. Okay, so this is called state space tree. So first I have taken the root node, then that can be colored in three ways. Again for each node I can color with three different ways. That suppose it is our node 1, so it is our node 2 suppose, so it again I can color with three different options. So that is 3 into 3. Again for that children I can again color with three different okay colors, that is 3 into 3 into 3. Okay, like this we have 4 nodes, so it will go up to 4 times. So total, so if you sum all this series, so you will get the series as, that is 3 power 4 plus 1 minus 1 whole divided by 2. So here you can say directly we can write, that is your 3 power 4 plus 1 neglecting all the constant factors. So it is 3 is your m or 4 is your n plus 1. So we can say the overall time taken for coloring a graph is at most it is m to the power n plus 1. So in this we have not used our this graph coloring or this technique. Okay, now it is the overall total how many ways we can have. Now let's try to color it with backtracking approach, how we use the backtracking in this. Okay, so here is the solution. So you can see solving the graph coloring problem using the backtracking. Okay, so we have three colors, red, green and blue. So the graph is same, 1 2 3 4, there are 4 vertices in the graph. So using backtracking, the time taken is at most m to the power n plus 1, it will be less than that, so at most it is that time. Okay, so there are many solutions, so I have written some few solutions for this graph coloring. You can see, let's try to build this state space tree and to get the solution better. Okay, more understanding way. So yeah, start. So suppose it is our first node number 1. Okay, so this node number first node I am coloring with, suppose red one. Suppose I am coloring this first node with red. So if I color this first node with red, okay, suppose it is colored with now red. Now so the second node, so the second node I can't color with red. Okay, so it will violate the property, the two edges not have the same color. So this second node I can't color with red. Okay, that means the only, and then go for next option, that is green. Okay, so can I color with green? Yes, we can color it with green, it is allowed. So two different colors are there, so green. Again for this node, for second node, now if we have colored with green, so how many possibilities are there? Can we color the third node with red one? See, can we draw the third one with red? Yes, we can draw. Okay, we can draw it with suppose red color, that is okay. Now again this node, this we have colored it with red. Okay, again can we color this fourth one? Okay, just a minute. Okay, just can we color it with again red? No, we can't color it with red. If you take red, so it will violate the property, so red can't be used here. Okay, again, so come back here. So can we color the fourth one with green? See, fourth one with green. Yes, we can do. So here you can see. So we got the first solution, that is red green red green. So the path is red green RG RG. So it is node number 1, node number 2, node number 3 and node number 4. So we have finally colored all the 4 vertices. So there are plenty of solutions are there. So again backtrack. Can we color this with blue? Let us try. Fourth one, if you don't take green, if you take blue, can we? Yes, blue is also allowed. So this is also the next solution. So first solution, what we got? The first solution we got was red green. The second solution is red green red and blue. Again this is the thing. Again come back to this one, this green. Okay, now similarly for this green, this node, that is of second node, can we color with green? See, already we have second node as green, so we can't color the third node with green, so it will violate the property. Okay, so can we color it with red? Blue. Take in this case blue. Third node, can we color it with blue? So let me erase this one. So let me erase this. So this is our so far. Okay, so we first node is at color red, second node is at color green. So we are taking the third node at blue color. So if you take blue, yes. So again, if it is we are coloring with blue, can we color with red? See, no, we can't color with red because node 1 had already red color, so it is violate the property. So red is not allowed. Again, can we color it with green? See, fourth node, it is a fourth node. Okay, yeah, green, yes, green is allowed because green is not adjacent. So yes, this is our solution. So this was our first solution, this was second solution, it is our third solution. The third solution is red green blue green. So like this we can have again we can backtrack and we can draw the complete this space tree structure, and you get many solutions, okay, for this given problem. So if you come back to this, can we color it with blue? See, the fourth node, can we color it with blue? No, already node 3 has blue, so we can't do this. Again come back to this one. Again we have the blue of can we color the second node with blue? Like this. So explore all this tree structure and you will get many of solutions. Only thing is that we have to remember is no two vertices can have the same color. So like this we can have many more solutions. So this, with the help of backtracking, we can have solutions for graph coloring problem. Okay, now what are the applications of graph coloring problem is? So first one is map coloring. We have suppose a map, suppose let's take the map of India. So we can color each and every state. At most is we can have the different colors, but we can have the minimum color if you want to color the states. No two states have the same color, so that we can differentiate between these two states. Okay, that can be done with map graph coloring for the map coloring. Next is bipartite graph. So if a graph can be colored in two ways, so that we can say it is the bipartite graph, otherwise we can the graph will not be a bipartite graph. So graph coloring also plays important role in bipartite graph. Sudoku games. So we have Sudoku games where each and every box is we can color with different colors. So to make it or you can use the graph coloring applications. Radio frequency, different frequencies we have, and we can to differentiate that frequency we can use some graph coloring technique or graph coloring applications. And lastly, as we know, coloring the academic calendar of any institutions or timetable of a class, we can have different colors. Okay, with the minimum colors we can color the whole timetable. So that is where we can use our day-to-day life graph coloring problems. Okay, so this is all about graph coloring problems. So next, move to the next applications of backtracking, that is called as Hamiltonian cycle. So what do you mean by Hamiltonian cycle? Basically means, so Hamiltonian cycle means given a graph having some nodes and some vertices and some edges are there. So starting from a first node, we are asked to visit each and every node of the graph exactly once and then return back to the starting vertex. If you are able to come back to the starting vertex, that is called as Hamiltonian cycle. Okay, so given a graph G from a starting vertex, if we visit all the vertices of the graph exactly once and then return back to our starting vertex, this is called as Hamiltonian cycle. So backtracking also plays an important role for finding the Hamiltonian cycle for a given graph. Now note point is here is that suppose if we are not able to come back to the starting vertex and we have traversed all the vertices of the graph exactly once, so that is called as Hamiltonian path, because we are not able to come back to the starting vertex. If you are able to come back to starting vertex, that is called as the Hamiltonian cycle. Okay, so it is also very important. Now here you can see finding the Hamiltonian cycle using the backtracking approach. How you can find the this one. Okay, so before this, let's take one example here. Okay, so suppose now let's take one example of a graph. Let's take some simple example. Suppose this node 1, this 2. Okay, let's take it 3, let's take it 4. So this is our graph, and let's take one more vertex 5. So let's in this graph G, so it is a graph G, the graph G. So in this graph having this 5 vertices, so is there any Hamiltonian cycle exists or not? So let's try to find out. So let's start with the node 1. Okay, we can go to node 2. Yes, again from node 2 we can go to node 3. From node 3 we can go to node 5. From node 5 we can go to node 4, then we can again come back to node 1. Here you can see we have traversed each and every node. All the nodes are traversed, and the starting and the ending both are same. So you can see both are same. So that means Hamiltonian cycle exists. So there can be many Hamiltonian cycle for a given starting vertex. Okay, so this is the thing. Here you can see. Let's take one more example of a graph. Okay, suppose we have node 1, suppose we have node 2, okay, node 3. Just remember, the repetition of cycle is not allowed. Okay, as the Hamiltonian cycle, it should be unique. Okay, all the path, all the vertices traverse should be unique. Okay, so 1 2 3, let's make it suppose 6, and let's make it 7. So here you can see, let's take this graph. Now let's start from vertex 1. Now from vertex 1, let's move to vertex 2, then move to vertex 3, then from vertex 3 let's go to vertex 4, then vertex 4 to vertex 6. Now if you go to from 6 to, we can go to 7. Now there is no possible way to come back to 5 and to traverse 5 and come back to 1. So we need to repeat the vertices. So we can say the only solution is, again, if you want to come back to the 5, the only solution is you will write here this 6 again. So it is not allowed, repetition is not allowed. So we can say in this graph there is no Hamiltonian cycle exists. Okay, so there is one note point here, please note it down. If in a graph if there is any articulation point, or we can say any pendant vertices, so that graph will not have any Hamiltonian cycle. Okay, pendant vertex means like this, if you disconnect it, this one articulation point means if you remove that vertex from the graph will disconnect. So that means that type of graph will not have any Hamiltonian cycle. Okay, now let's try to find for this given graph, let's try to find the Hamiltonian cycle. We are using the backtracking approach. Okay, for finding this backtracking approach. Now again the same rule applies. We'll make a state space tree. Okay, to get the what are possible solutions we can have. So how to draw the state space tree? We start with the first vertices. Okay, that is node number 1. From 1 we are starting. Now from 1 we can what are different total nodes are there except 1. So in this except 1, how many nodes are there? We have 2, we have 3, we have 4. Here you can see if you take 1 in the graph, node 1 in the graph, so all the 2, 3, 4, all these nodes, so we have total possible. Okay, let's see if there is an edge or not between this node. From 1 to 3, see, yes, there is an edge. So yes, that means we can go to 2. Okay, let's first draw the left first, then we go to rightmost. Then we have reached to second node. That means we have traversed from here to here. Now from 2, what are different possibilities are there? Either we can go to 3 or we can go to 4. Remember, since 1 and 2 are already covered, okay, so 1 and 2 are already covered, so we have two possibilities. Either we can go to 3 or we can go to 4. Let's check from 2 to 3. Node is there, path is there. Yes, there is an adjacent path 2 to 3. Yes, so that means we can go to here. Now from 3 again, we only left option is 4, so we can go to option 4. That's we can say node number 4. Check whether 3 to 4, from 3 to 4 path is there. Yes, there is a path, 3 to 4 path is there. Again from 4, check whether we are able to get back to our starting position. That is the Hamiltonian cycle we will get. Okay, yes, we can get back to our node number 1, so that is we can allow. So this is, that means we got the cycle. So what path we got? So the path we got is 1, 2, 3, 4 and 1. So like this is our first path, okay, that we have got here, the first solution we can say. Let's see if there are any other solution do exist for this given graph. Again, for from 2 to 4, is there any path? No, there is no path from 2 to 4. You can see in the graph. That means this is our bounding condition, so we can neglect this. Okay, we will remove this. Now again come back to the this 3. Suppose we traverse from 1 to 3. Now suppose we traverse from 1 to 3. Now 1 to 3 means again we have two possibilities. Either we can go to node 2 or we can go to node number 4. Okay, so check whether 3 to 2 path is there. Yes, path is there. So again for 2, the only possibility left is node number 4. See whether we are able to reach to node number 4. 2 to 4 there is no path, so don't consider this. So it is a bounding condition. So we 2 to 4 there is no path, you can see in the graph. Okay, that means we have reached to dead end, so we are backtracking. So this is called as backtracking. Okay, again for this 4, we are at 4, node 1, node 3, node 4. The only solution left is 2. Okay, let's check for 4 to 2 path is there. No, there is no path, so this is a bounding condition. Just neglect this path. Again backtrack. So I think 3 is done. Traversing from 2 is done. Traversing from 3 is done. Let's traverse from 4. Suppose we are traversing from 1 to 4. From 1 to 4. So path is there. Yes, path is there. Again for 4, similarly, what are possibilities we have? Either we can go to node 2 or we can go to node 3. Okay, so this is there. So so find 4 to 2, there is no path, so this is our bounding condition. Again it fails, so we can neglect this. Okay, because there is no path over here. Okay, 4 to 2. Again 4 to 3, yes, there is a path from 4 to 3, so we can traverse 4 to 3. Then from 3, the only solution left is we can go to node 2. Check from 3 to 2 path is there. Yes, path is there. So that means this is our second solution. So what is our second solution we got? So our second solution is we can that is our 1, starting from 1, then we traverse 4, then we traverse 3, then we traverse 2, then we traverse 1. Because from 2 you can see we have the 1 also. Okay, that's why we got this Hamiltonian cycle. So that means this was our first path. So the solution for the second is we have 1, we have here 2, so we have a 3, and we have here 4. Okay, this is our graph. Now so 1 to 4, yes, then 4 to 3, yes, then 3 to 2, again we got the path, 2 to 1. Yes, you can see all the vertices of the graph is visited exactly once, and we got the cycle also. So in this, for this given graph, you can see only 2 Hamiltonian cycle is possible. So with the help of backtracking, we can find how many possible Hamiltonian cycles are there, okay, for a given graph, with the help of state space tree. So with the help of this kind of tree, we can easily find we can say Hamiltonian cycle. Okay, so thank you so much.